Our next presentation comes from Michael Stephan from Leibniz Supercomputing Centre.
First, one slide about what LRZ is and does. So at the moment we are around 200 people. LRZ was founded in '62 initially as IT service provider for the Munich University. So we run email servers, VMware installations, all the network in the Munich area for the universities. Later that was expanded to services for Bavarian universities, and then we became one of the 3 national supercomputing centers in Germany, which are now in the DAOS center, and we also participate in European projects. So today I want to focus on our actual HPC system that we host. So the system was procured 2018. Procurement was even earlier, but the procurement had a 2-phase installation plan. Phase 1 of SuperMUC was installed in 2018-19 timeframe, and after some early adopter production went into full operation in 2019. So it's a fairly standard CPU-only system based on Skylake with 2 types of storage tiers, one high-performance storage for work and scratch, and a little bit slower data science storage, which is for more long-term storage of project data, and is also available for experimental data groups which want to ingest data they can analyze later. I think the most prominent and special at that time was that the system is the 2nd generation of direct warm water-cooled systems. So those 2 storage tiers are based on traditional GPFS, and part of the 2-phase contract, so when the initial contract was signed, the proposed 2nd phase was based on Intel's Knights Hill architecture, which after some time was dumped. And so we started a long and winding trip down from the hill and towards Ponte Vecchio with some delays, detours, and so on. So, but the system is fully installed, is in place. So we have 240 nodes. Each with 2 Sapphire Rapids CPUs for Ponte Vecchio GPUs, 756 gigs of DDR5 and HBM2 memory per node. And additionally, some high IOPS storage tier, which is based on DAOS and another technology Intel already dumped. So we have still an Optane-based installation there, which was sitting for some time and waited for the compute to arrive to be used. And honestly, when I thought about the title and handed in the title for the agenda, I was I really thought, well, I would be here and present first results, but unfortunately we are still in early adopter phase, and the acceptance isn't finalized. So I thought, okay, let's recycle the title and talk about a different project. So Terabyte is a collaboration project which we implemented for the last 2.5, 3 years to provide a high-performance data analytics platform for Earth observation community. So Earth observation community, so these are the people that collect all the data that comes from tons of satellites that are out there orbiting around the Earth, collecting data on a huge variety of physical spectra, gravity, and so on. Combine it with measurements they do on Earth, on plane-based measurements, and also on, and then combine them to get a deeper insight in the state of the Earth on global scale, but also on local scale. So one example of that is flood monitoring. So they have the raw data that's coming from various amount of satellites that orbit the Earth. Then all that raw data is ingested into a complex pipeline where in the end, after combining all that data, they produce variety of deliverables which they can then hand out to customers. So typical products, as they call those results for the flood monitoring, are more long-term drought monitoring. So you know how much humidity is in the ground, so you can estimate how crops grow. Anomaly detection, so reference mapping for planning where to build or where you should better not build stuff, but also time-critical products like rapid flood mapping or flood monitoring, predictions, if the level rises, where it will go, so that this can then be handed out to companies, state agencies, or politicians for decision-making during a crisis. And so with more and more satellites that are in orbit, producing data of higher resolution, so the amount of raw data that comes in is growing, and as you've seen with the huge amount that has to be computed, also on a time-critical basis, the amount in data storage and compute facilities also grow for that community. So back in 2019, the DLR's, which is the German Aerospace Center, so the DLR's Earth Observation Group reached out to LRZ and proposed a collaboration between the two institutions to build and provide that facility to the Earth observation community to deal with their growing demand on resources. So after all the legal stuff has been put out of the way, in 2021-22 we started with installation of the first storage, so they could start bringing in all the satellite data, then added the compute facilities and so on. So we could really do the official launch of the whole platform in mid-2023. So the collaboration is managed in the way that the funding for the hardware came from DLR. LRZ is hosting and operating the hardware. And from the software and service perspective, we do more the basic infrastructure stuff, and DLR focuses more on the scientific Earth observation stuff. So these are the building blocks that are in place at the moment. DLR is doing all the support because they know their customers and the codes. They also provide the metadata catalog to help the researchers to find the data and filter the data they want to use. LRZ is responsible more for the storage, the HPC part, also the whole identity management as the hardware is integrated into our infrastructure. And for example, the compute portal, this is one area where we collaborate and both sides participate into the project. So one example, metadata catalog. This is typically the first step where a user goes to see what raw data is there. So what can I have on the online storage? Or if the data is still in a tape archive and has to be brought online for the analysis. So this is where they select whatever data they need, which they can use for whatever workflow they have and they want to implement. One thing that also was in the discussion early on in the project is that a lot of those workflows are developed on modern cloud infrastructures because it's easy to develop your workflow there, just throw it on there, let it run, do the development. But after all, then they fail. Well, when the workflow is developed and they are confident, then they have the issue to bring in the real data they want to analyze. So they have to move the data back and forth between cloud infrastructure and the satellite data archive and so on. But they are not the typical HPC user. So what we also focused on is to bring over these more cloud-based technologies into a more traditional HPC environment so that they can bring their containers over from the cloud and run them using Charlie Cloud or en route at the moment. We also provide graphical user interfaces into the resources using on-demand. And also a huge project is to extend the open EO application suite to be able to leverage Slurm REST API to spawn the workflows in the background so that people still use the front end and don't even realize that in the background there is a traditional batch job spawned, and then they see the result of that calculation. So the web interface, which is based on Open on Demand. When you log in, so at the moment this is what you see. You can run your traditional batch script in a very traditional way with it, but you can also just click and spawn a Jupyter notebook on one of the compute nodes. You can run even a remote desktop based on NoVNC, metadata catalog, and this is really a growing effort to bring more and more of their typical applications into the Open on Demand web portal to make the transition as easy as possible. So if you look on the whole infrastructure from a little bit more technical view, so in the center is really the online storage, where all the satellite data is stored and then ready to be analyzed on whatever the user needs. So the storage is connected via InfiniBand or some of the cloud parts via Ethernet to the storage. So we have a huge more HPC partition, but also some cloud nodes there. We installed a dedicated link between LRZ and DLR's tape archive, where they have all the historical satellite data. So if people needed to analyze some more time series, like in, for example, glacier development analysis, they can take the data from the archive. Data that is actually that comes from satellites can also be ingested via our standard research network internet connection from ESA, NASA, and other sources, which provide those raw satellite data. And then everything is collected on the storage and can be processed. So from the hardware side, the storage, it's at the moment roughly 50 petabytes of online storage, which is also GPFS-based. Part is Lenovo's DSSG, another part is IBM's ESS, where I think 6 petabytes are for users for their project data. The rest is really for raw satellite data that is curated and downloaded by DLR staff. And as a compute platform, at the moment we have those roughly 300 nodes, CPU-based ones, also roughly 50 GPU nodes equipped with A100 GPUs, and all connected with a HDR InfiniBand fabric. So yeah, the two external connections I already mentioned. So from the HPC perspective of view, well, it's fairly nothing fancy, nothing huge, but for the Earth observation community to have that amount of compute combined with a large online store for all their data is really a step forward, so they don't have to shuffle data back and forth from the tape archive then to the cloud, throw it away, then for the next run just put it down again and so on. This is more for reference. So from the beginning, we implemented a lot of stuff, prepared all for the operations, especially the support, because especially in the beginning, users that are not familiar with HPC have a lot of questions have to need some training. But there is still stuff on the roadmap. And one thing I want to focus at the end is, so what we are doing right now is setting up a Kubernetes-based service, which will run on the same hardware as the HPC stuff. In the first implementation, that will be only open to the application groups within DLR, so that they can deploy their services on that Kubernetes infrastructure to then make that application based available on the for the users. But later we maybe will also implement user Kubernetes clusters, so that users from the community can manage their own Kubernetes cluster. And one important point here is, because that's a new service for the community, and well, we are not sure how they will use it, how the demand in the end will be. We really decided to have the same nodes that we can deploy as standard HPC bare metal nodes, to use them as Kubernetes worker nodes, so we can scale up and down depending on the demand that we will see on that side. I think in the beginning it will be manual scaling up and down, but if we see that there is some need for automatically switching from standard Slurm node to Kubernetes worker, maybe we will also automate that. Okay. Thanks. Any questions?